Yes,
Okay. Good morning. We can get started. So how is everyone doing this morning? Did people try to log into those machines? Were you able to log into those machines and started the projects? I noticed a couple of you downloaded stuff, and I'm guessing things are working fine. So, but if you haven't started, get started soon, because most of the software projects you might have seen from the past don't react the way you think they should. And it's especially true for when you're trying to compile operating systems and stuff. If you're not done that, if you don't know the intricacies, right? There should be none, but you never know. So get started as soon as possible. If you run into any problems, talk to me or the TA. Right? So how are we doing so far with the lectures? Are we going a little slow, or we're kind of going a little slow towards the beginning of the class? I think towards the end we'll kind of pick it up a little bit. I think the problem right now is trying to define what the operating systems are and trying to place these things in context. And once you get going, I think it'll be a little faster, right? But if it's going fast anytime, too fast, let me know. We'll try to work on that, right? So I would like to continue on with where we kind of left off. Right? We are looking at the CPU scheduling and looking at processes as a container for running a program. So a program is running, we call it a process, and the kernel represents that using process control blocks or PCBs, and all the resources which are allocated to it, CPU and memory and all those things get, they have entry in the PCB, and the kernel moves them around different queues. So essentially what the operating system is trying to do is juggling these things, juggling the ready processes in such a fashion as to achieve some goals, giving good interactive performance or things of that nature. And throughout the course, we'll go into more detail on how these little different things affect us. So the next little item on the process stuff is how to create a process. Right? We talked about processes are these things which encompass all the resources associated with the running program, right? And to create a process, once you create a process, the kernel will allocate the PCBs for it. The entity which creates a process is usually a process, right? So when you boot up the kernel, magically process 0 starts. And process 0 then starts process 1 and so on. So all the new processes are created as children of an existing process. And so you kind of tend to create a tree. So when you log into a computer, there's a shell or something running, and any new process you create is a child of that previous process which is running there. And so when you create a child, there are different ways the child can run. So you're creating a new process, and so now there is a parent-child relationship. There's a parent which created this process and a child which runs. There are some tasks which are always done by all parents. A parent should be able to kill a child. Parent should be able to get rid of a child. No. Not in the sense, but in the computer sense, right? So the parent should be able to control the child, because it's somehow giving the resources. There's no human thing involved here, just the operating system sense of parent-child. So you can imagine the child sharing all the resources of the parent, getting a copy of all the resources, or no sharing at all, right? So If the child shares all the resources of the parent, then the child gets to modify the resources, so it can close the file. You can operate on data which will affect the parent. The child can get a copy of what the parent has with some things being shared, right? Where certain aspects you get a copy, so you get to modify them, but they are not reflected back on the parent, right? And some of the things you share, some of the things like your standard output, input, output, and all those things you share because you want to output to the same device. But there are other things you don't get to share. You get a copy. And there's other mechanisms where you can think of no sharing at all. A child gets created and it gets nothing of what the parent is trying to do. And different operating systems implement different versions of these, and each of them have their niceties and bad things. The child sharing everything is good, but child sharing everything also means that the child, you have to kind of trust it in a certain form. Otherwise, the child can mess up the parent. The execution model. So once you create the child, you can imagine either letting the child run independently along with the parent, or the parent stops after the child finishes. The parent can continue, right? And different operating systems tend to do it differently. And so when you create the child, you can also imagine being either creating a duplicate of what the parent was and then trying to let you figure out what to do about it, or the child is a new incarnation. It does not share anything. It also gets its new address space and new process and stuff, right? So, for example, Unix follows the model that when you fork is a system call for you to create a new child. So when you create a new child in Unix, right, the child gets a copy of all the stuff that the parent has. So the parent and the child looks exactly alike, except for if you try to find the parent, they are different, right? The parent of the child is the one which created the process, and the parent of that process is something before it, right? So except for the parent relationship, the two processes are identical. So they get a copy of what was in there when they split, right? They share the file descriptors. We haven't talked about what they are, but the basic idea is any I/O that you're doing, you both get to do the same I/O on those, but you don't get to change the variables. The variables are disjoint now from that point on. So if you want to start a new program, right, many times it's not that much fun to create a clone of yourself. I mean, it basically does the same thing as what you're doing, and they're both going fine. So you would you would use something like an exec system call, which basically loads a new program and runs them. So if you want to create a new program, right, if you're writing a shell or something and you want to start a new program, you would exec, you would fork, which will create two clones of yourself, right? And one of the clones would, the child clone would do exec, which will load a new program and be different from that point on. Once you exec, that's a different process. Till it's different process, they both are the same program, kind of running in parallel, right? Windows XP supports the other model where when you do the equivalent of fork, you have to specify what program you want to run. So it basically, when it does a fork, it also creates a new process, right? And each one of them are useful in their own sense. Most of the Unix programs would probably do the fork and exec and start a new program. But there's some times where you want to fork two processes and have them both run the same program, right? For the most part, you don't want to do that because there is another abstraction called threads, which we'll see later on in the class today, which will do the much better job of just forking without execing kind of functionality, right? So these are different things you need to worry about when you're trying to create a new process. You want to create a new child, you have to figure out what to give it as resources and what kind of a sharing it wants to do with the child and with the parent, and how the address spaces are getting created. And again, depends on the operating system on how they want to do that. So once you have the process creation, you have the process termination, the exact opposite of that. So process termination can be initiated by the process itself by calling the exit system call or equivalent, right? So when a process finishes, it calls the exit system call, which cleans up all the kernel data structures for the associated process. So it cleans up the PCBs and what have you, releases all the resources, right? And releases locks and stuff. We haven't talked about what locks are, but as like all the things that the kernel knew about this process has to be cleaned up, right? And there is one other task the process wants, which is notify the parent that it's left, right? So far I said, when you create a fork system call, you create two processes and both of them are running independently, right? And the parent wants the ability to control the child, wants to kill sounds kind of wrong, terminate the child, or it wants to stop the child or do things with it, right? But if the child does not let the parent know that it's gone, then the parent cannot control. So the one way for the parent to know what's happening is through a wait system call, right? It can find out what's happening to the child. It can wait on the process of the child and stuff. So when a process exits, the OS may not just release everything. Right? It at least has to do something to tell the parent that this process is gone, right, before it can fully release these resources. Can you think of a reason why you would want this stuff? Why you would want to have this parent do this stuff? Can't you just find out later on, right? So what I'm asking is, if you do a fork, right, and suppose you have no mechanism for the child, for the operating system to say that the child is gone, right? When you create a fork, the parent knows what's the child, right? It knows the some ID, right? Let's call it process ID, some number to know what the child is, right? So if the operating system lets the child go away, right, and lets the process come back after a while and look at the status of the number it has, of the ID it has, to see if the child is still around, right? And find the status of that. Why keep track of this, right? Why would you or why wouldn't you want to do that? Yes?
The operating system can allocate resources, and the parent, if it doesn't know the status, doesn't know that it's there, then it could call the child process, which is no longer there or not running, and then produce errors in the parent program, something like a web server or something, running child.
So yeah, one of the points is the parent can give errors because child is no longer there, right? So can that be solved by finding out, doing a dynamic query, right? Trying to find out what the status of the child, right? So before the OS does anything, it looks up the status of this process ID or something and return that. Most modern operating systems would not do that, right? What they would try to do that is they'll create a process in a zombie state, right? If you looked into Unix and stuff, you may see some processes in the zombie state where they cannot be killed because they're waiting to give their status to the parent before they go away, right? So they cannot be killed, they don't use any resources, but they just still hang around, right? So one of the things that you want to avoid doing if you're doing this dynamic lookup, dynamic trying to find out what the status of the child is, yes, you won't find the return value of the child. If the child is trying to return some value, you won't find it. And the OS is free to to reuse those resources, reuse these PCBs, reuse stuff for whatever it wants, right? So the process, the parent cannot hold on to some number and say, my child was process 10, right? The child is not process 10. Whatever incarnation was running was the process 10. But once the OS completely releases all the stuff, it's free to do whatever it wants. So it can allocate that PCB to some other new process. So you can't, you have to keep track of those two, right? So there are some reasons why you want to keep track of these. So these are all happens for processes which exit normally, and there are reasons why you exit abnormally, either because of the fault of the child or fault of, whether it doesn't have enough resources. So if you call memory locations which you're not supposed to call, you get segmentation fault or whatever different versions that your own operating system would give. So you probably notice processes dying and giving some errors, right? In Unix, you tend to get a segmentation fault. In Windows, I think that these days it brings up a window saying your process quit. Do you want to call back to Microsoft or something like that, right? So that happens because there's there's an error with the program, either because the programmer wrote wrong or some resources went away. And it could be because the child is exceeding its resources. So if it's using more resources, then the parent or the operating system can kill you, saying no more resources. And the other thing you need to worry about is what happens if the parent exits before the child, right? Some operating systems expect the parent cannot go away; it has to wait for the child, and some operating systems let the parent go away, and the child be inherited by the operating system or the process 0, right? Again, there's no one right reason, right way or wrong way, but different operating systems do it differently. Unix tends to, if the parent goes away, the process will be inherited by the root. If you don't do that, if you have to have the parent around, then you have to leave the parent in a zombie state. So if the parent dies, then you have to kill the children and stuff. So these are different problems that you need to worry about when you start worrying about processes and how to allocate them, how to terminate them, and all those things. And as we go through the different components, some of them will become more clearer. One of the things I mentioned was the logs and stuff. We haven't talked about that. That's in the next module. For now, the processes are independent, but in reality, they're not independent. They depend on resources which are shared by other processes and stuff. So they have to wait till they notify others and get status back. Right? Which is sort of what we are trying to say here, even though more of the details will come along as we move along in the semester, right? So a process is a running program. If a program does not share anything with anything else, it's an independent process. It can finish its task. Every process has to depend on its parent for giving status and stuff. But for the most part, it's independent by itself, right? And that's well and good for some kind of applications, but most applications would like to share something with other processes, or many interesting processes would like to share something with another process. And there are mechanisms which allow that such kind of a cooperation, where you want one process, another process on the same machine to be able to share something, cooperate on some things, but be independent on the other. I mean, they get their own CPU, they get to run on their own resource management, but they also get to share some of the stuff. And this sort of a programming is typically called the producer-consumer problem, right? Where you have two cooperating processes, one creates something, the other uses that, and then it proceeds. So the first one runs for a while, creates some output, then the second one uses, and then goes along. It doesn't have to be like always one produces, always one consumes, but basically they are cooperating. One does half, the other finishes the rest of the half. And as we move along, we'll see what are the issues in trying to make this coordination. You want to make sure that after I'm done, I give the whatever my half to the next one, and then it should go. And you need to have clear-cut ways to say when I'm done, when you can start, and stuff like that. But the idea is once I'm done, I give my task to the next process, and then it goes on. And there are a number of classical problems we named here. One of the things is the producer-consumer problem. It's a traditional operating system problem. You have producer and a consumer trying to share something, and the real issue involved is how much of a buffer do we have in passing this task, right? You can either imagine unbounded buffer, right? Where I'm the producer, there's a consumer here. I can keep producing however much I want, and I can just keep sending it over, right? There's an infinite buffer here, so I can keep running at breakneck speed, send all the output to this one, and then have the consumer read off of it. The reality is not, you cannot build unbounded buffer, so you have a bounded buffer problem. So you have a certain amount of buffer space, so I can keep going as fast as I can till this thing does not fill up. If it fills up, then until somebody takes stuff off of it, I cannot proceed, right? So the mechanisms of how we do that we'll see as we progress. But basically the problem here is you have two processes. Each of them are independent. Each of them can do whatever they want, but they depend on each other because one produces, one consumes, and they're sending it through a buffer. And how you manage the buffer for those, right? But you can also imagine two ways of sharing this stuff. One of the ways I said was to do explicit, like what I mentioned was, like you send this message over kind of thing, which is more of a explicit what is called message passing. I have the results, I give the results over to the other process through a message or through some mechanism, and in the first one, process A finishes something, gets the partial results and gives it to the kernel, and the kernel somehow knows how to give it to the next process, process B, and then they proceed, right? You can also imagine a shared memory model where these two processes now share some memory region that they can both write simultaneously into them, right? As we proceed along, again, we'll see how the sharing happens, right? Because the operating system has to make that happen, because one of the first tasks of operating system is to protect processes from each other, right? So you want to protect process A from process B and process B from process A, but over here you are trying to create a region which is shared by both. So you have to now unwind some of the protection so that they can both write into this little section, right? Even though that could potentially be harmful. So process A has to initiate something, process B has to initiate something. The OS has to negotiate these two such that they can now share this little space and not do more harm than what they asked for. Right? So these are the two big paradigms of sharing stuff. You can either have explicit message passing or have a shared memory where one process can write something, the other process can read something off of it. And so in the second model, after process, there's some notion of after process A, right? Somehow magically, process A finishes its task, writes into the shared memory. Process B somehow knows that, when to read the data off of the buffer and then proceed. And again, we'll see how those things can be done, and one of the ways is through locks and other mechanisms. Right? So going back to the message processing model, the shared memory model requires more knowledge that we'll see a little bit later in the class. With the messaging model, right? Again, there are two different ways to do it, and I'm not going to at a high level. So if you have two processes and process A wants to send to process B, right? You can either have it sent as, so you need to first have a way of naming stuff, right? I call them process A and process B, but you need to have a way of implementing that in the operating system. So it has to be something like a process ID or something. So you have to first define how processes are named. You have to first define how this name will be known to everybody, right? As is, most processes do not know about anybody else. Now I have to have a way of figuring out what are the other processes, what is the process that I'm cooperating with, and what is the process's name, right? Suppose I know that, and suppose I know that P and Q are trying to talk to each other. So P knows about Q and Q knows about P, right? Then you can think of a system call send and receive where you specify the name of the recipient. So if you want to send to P, right, Q would say send P message or something of the sort, and Q would have the receive function, right? So to implement that, you have to somehow know what the other processes are, and you have to trust the other process, and they have to cooperate. And that's not usually done by the operating system. You know, somehow you know that. You have to know who the other processes are and who you're cooperating with, and send this stuff. And typically, it's a single link. So you have one producer and one consumer, and you have to send this message between these two, and they both have to initiate that. Both of them have to say, I want to be part of this communication, and they can send and receive this process. As you may imagine, if you're trying to write this as a C program, right, now you have to write a C program where you're writing one program, and you know that another program exists, right, which is running at the time of you starting this program, and you have to send this process. So you need to have all these names and stuff, you know, ahead of time. And an easier way to do that is through creating an indirection where you don't send it to the next process directly, but you send it to an abstract name, right, which you kind of compile into the code. And one example of that is what Mark, or the operating system which runs in your Apple OS X, calls mailboxes, right? So the idea here is, when I develop the process, if I want to communicate between two applications, I create a new mailbox or a name, right? So I say this project will be called operating systems -Surendar, right? And that's the name of the communication that I want to do. So whatever I want to send, I send it to this abstract mailbox, and whoever wants to receive would read from this mailbox. It behaves very similar to your, your email. You don't wait for the recipient to read the email. You send the mail to their version on the system. You know, and if I want to send a message to somebody in class, I send it to their mailbox. It's stored on the system and delivered whenever you get there, right? So this is a more useful way of doing these things. All I have to do is a priori decide what the mailbox name is, right? And somehow all the applications know about it, which is a lot easier because I'm the one who's writing the program, so I know all the different applications, and I give them a name, right? So whenever I want to send something, I send it to this mailbox. Whenever somebody wants to receive, they'll receive from the mailbox. It's a powerful paradigm. Now it lets you have many recipients, right? You don't have to say there should be only one recipient. So if I have a mailbox, any number of users can read off of it, like your email mailbox. You can read it from your, from web browser or other mail clients and stuff like that. And so once you have many recipients, you have to worry about other stuff. You have to worry about who gets it, which of the clients get it. And before we do that, we also look at when I'm doing message passing. So these are different things that you need to worry about if you want to have two processes communicating with each other, right? So first thing we looked at was how to name who we are sending this stuff to, and we need to worry about how much buffer space to have for sending those things. And we also have to figure out how this communication would proceed, whether it's blocking or non-blocking, right? All these terms will come back and back again in different contexts, right? The idea here is you can do operations synchronously or you can do operations asynchronously. Synchronously means if two of them are cooperating, right? The sender can wait till the receiver receives it, and only when the receiver receives it can the sender proceed, right? And the receiver can only proceed after the sender sends something, right? So in that model, if I write something to a mailbox, write something to a message system, till the receiver receives it, I cannot proceed. Whereas the asynchronous model is, I don't care. As a sender, I just send it and then I keep moving on. As a receiver, it can wait for data, or it can just return back saying, I have no data here, right? So these are the two models of programming. You see it in this context, and you'll see in other contexts. Have you seen these asynchronous and synchronous modes of operations before in your C programming class or something? If you haven't, you'll see a lot more of it as we move along, right? The synchronous mode of operation is a lot easier to understand. It's probably what you've used so far. When you do a read system call or any of the other I/O operations, you expect the data to be there, right? You expect the data to come back before you proceed. When you do a write, you expect something to have happened. You don't expect to keep remembering what happened when you did a write, right? When you write your C programs, I'm assuming you wrote, write, and then you closed, right? You didn't have to wait to see what might have happened to the write. Is that true? Right, in your C programs, you never so once a system call finishes, once a line of code finishes, you don't expect something to go wrong afterwards, right? If you have 4 lines of code, you finish line 1, and then you come to line 2, then you come to line 3. When you're at line 3, you expect line 1 to have completed, done with. You don't have to go back and look at stuff, right? Such model of programming is easier to understand, but it's also very slow, right? It's also very slow because you are more made to wait for every little thing. So most of the applications that you would do, in real life, would want some kind of a asynchronous model, right? Where you don't wait for the operations to finish. You start the operation, then you move on, right? And then you wait for the status before it has to be done, right? Before it's important. Till that point, you kind of tend to go, right? Has any of you used asynchronous I/O for any kind of stuff? If you haven't, this is something that you will see more of it in the class, and more of it in your upper level classes, right? It's a little harder to program because you have to keep track of. So application has to keep track of all this stuff. It has to keep track that this write that I did a little bit back may not have completed. So I may get notification later on that some writes completed and I have to do something about it. But it gives you better performance. So most applications that you'll write in real life would want to use asynchronous I/O, right? And so that's the notion here. So you can imagine. So if in the first case, if the sender has to wait for the receiver to receive it, right? That makes writing the sender very easy. Now the sender knows that if it gets a return value saying somebody has read it, it knows for a fact that everything is good, so it can proceed, right? But it's also slow if the receiver is not keeping up. The receiver is slow, right? The sender is only going as fast as what the receiver can do, right? And that's usually not very interesting, right? Think of this as if you're sending a SMS message to your friends, right? If you expect, once you send an SMS message or once you send an email, that till your friend receives it, you cannot proceed, right? Sending an email to this class would be very hard, very boring, right? I have to send to each one of you and then wait for somebody to come back and say they got it, right? And that sequential processing tends to be very slow, right? What asynchrony does is allow you to do some things in parallel. So I can send email to different people, right? And then at the end, wait to see if everybody received the email. Things can go in parallel, right? And we are slowly introducing the notion of parallel computation. And one of the most powerful ways to do that is through the asynchronous mechanisms, right? So I'm introducing a lot of terms, and we'll use more of them as we move along. So bear with me if you haven't heard of many of these things, right? So the last thing, was so if I have a buffer, if I'm sending through a mailbox, right? So you can imagine, different ways of implementing this, and some of them will make it behave asynchronous or synchronous. So if I have a zero capacity buffer, right, every message I send has to be received by somebody because there's no buffer capacity. Unbounded capacity would mean that the sender can go at whatever speed it wants, but reality is you have to implement bounded capacity. Machines have finite amount of resources, so basically anything you send, there's a certain amount of memory so it can take. So after a certain amount of writes, after amount of sends, nobody reads it, then the process will have to be made to wait, right? So what we are trying to introduce with all this stuff is, from an OS perspective, OS does not care what this communication mechanism is. All it cares is processors give it some messages, right? It has to guarantee some kind of a buffer to store them. The buffers may get full. If it gets full, then it has to do something. It has to either stop the sender or kill the sender or what have you, right? So the state that it manages for doing this communication makes it more complicated. It's not a simple, I send the message and I'm done, right? So the OS has to now say, I'm allowing process A to talk to process B, which means that now I have a notion of a process A or process B. I have this notion of names, right? And I want to make sure that they can communicate. I'm guaranteeing that when they send something, I will either buffer them, right, depending on what I'm promising you, or I will stop the sender, right? If I have infinite buffer capacity, then I can do this, or I'll let you go for a while. When my capacity is full, I have to make you stop. So the state diagram we looked at before, right? There are more reasons why you could be put on the ready queue or waiting queue because of these other mechanisms, right? And towards the rest of the course, we'll see a lot more technologies which will make some of these things more concrete. Like, we're talking about sharing and stuff, and the stuff we'll see next, threads are a natural way to implement this sharing, right? So is that kind of clear? So that kind of leads directly into the thread model, right? Thread is something that we add to the process, and so it's kind of it follows along quite nicely. The notion of a thread, we kind of implicitly had it, but we never spelled out when we talked about processes, right? Processes we talked about, we somehow keep track of all the resources allocated to a running program or process, right? We talked about, we alluded to memory and all those things. But we never explicitly said how we do that for CPU, right? So we assign a CPU to the process when it's running, right? And that is a thread of execution, right? You have a thread of execution going into your program. When you assign a CPU to it, it gets to make progress on the CPU. So in the process abstraction we are talking about, we were thinking of one single thread of execution, one single program counter, one single thing which is happening, right? But there's no reason why you have to stop it with one. You can have multiple threads, and that's the notion of a thread. So the notion of thread is basically, you have the same thing you had before. You have a process, memory, all those things you talked about before, but now you are letting multiple threads of execution, multiple things to happen within the same address space, right? And all these threads share everything else. They share the address space, they share everything else, but they are ways to assign more than one CPU to the same process, right? And so if you look at it that way, it's not that different, because before we could assign multiple devices, multiple IO stuff, and now we are saying this is a way to assign multiple CPUs. So if you assign multiple CPUs to a process, each CPU will be doing different things within your process, right? And we call them threads of execution or threads. So sort of, pictorially, that this is what happens. So the process we talked about so far, you had all the code data files and all the stuff on the top, and you had single thread of execution where that thread has a program counter, register, stack, or what have you, right? But you can imagine having multiple threads of execution where different threads, right, they share the same core data and files, but they also have some private data so they can do different things, right? So have you guys programmed with threads before? If you use Java, you probably use threads quite naturally, right? So you guys?
Yeah, I wrote a small client-server program that could spawn multiple.
Okay. In Java? Or?
In Java.
Java, okay. Has anyone else tried threads in Java? Java. In many of the programming languages, you use threads without actually knowing about it, right? The cool thing about threads is you don't have to know about it. And I'll show you why, right? Many of the system calls, or what do you think our system calls, may spawn threads to do what they have to do. But the threads get to share everything else. So they basically wait to get more CPUs, right? So the benefits of multi-threaded programs are, one is responsiveness, right? So now I have a way of assigning more CPUs to the same process, right? So potentially I could make your process go faster, more highly responsive by having multiple threads. So for example, if you run on, if I could give you 2 CPUs, right, your text editor may become faster because one CPU or one thread could be taking your input, another thread could be doing a spell check or rendering or something else, right? So you could suddenly see your system be more responsive because if you give it more CPU, then it can do multiple things at the same time, right? And for the text processing, it happens naturally. Whenever you press a key, right, you want something in the back, some thread in the back doing spell checking, grammar checking, or what have you, without stopping what you are doing. So there is multiple tasks happening at the same time, right? Resource sharing, that's the topic we'll kind of spend a little bit of time on. You know, the thing I talked about before, I have to know the name of the process I want to share tasks with and all those things, means that I need to know like names and all those things. With threads, it's very easy, right? All the threads share everything. So I can have 2 threads, they both share the same variable. There's nothing special I have to do. So it's very easy to do sharing in threads, right? In fact, it's way too easy, so we'll see how we'll make it a little harder so we can actually do something useful, right? It's very easy to just go and trash your own memory with the different threads, but you don't want that. You want them to cooperate, and how we do that is through the primitives. Again, resource allocation over here is pretty fast because they all are, you have one PCB, so creating a new thread can be as simple as adding some entry into the PCB, or even better. Sometimes the PCB itself won't know that you have a new thread, and we'll see how that happens. So it's very easy to create a new thread. It's very easy for threads to share data amongst themselves. It's very easy to use threads to add more CPUs. So if you have more CPUs, then the thing goes really fast, and that's the key. So if you suddenly move from a single processor to multi-processor machine, if you want your process to become twice as fast or what have you, threads are the way for you to implement those, right? And just a few years back, this concept used to be something that you do on a server, multiple processors and stuff, but most of the modern stuff that you buy are moving towards dual core or multi-core, right? So this is the hardware, hardware guys cannot keep the machines going faster and faster, so what they're doing is putting multiple processors inside a single chip. So that allows when you buy any of these new processors, you get 2 processors on the same chip. So if your program was multi-threaded to begin with, then your program will be twice as fast, or how many, depending on the cores that you get. If you don't do that, then your process won't be any faster. You're using only a single core, right? So so threads are becoming more and more important as we go, as the hardware kind of changes, right? So before I go there, something which is not in your syllabus. So last week, I was out of town and I was talking to the guys who are developing the Sony PlayStation PSP3, the next version, right? How many of your game players? or maybe follow what's happening with the PSP3 and Xbox and stuff. I'm not a game player, right? But I find the hardware cool. I wish I suck in game playing, but I like the hardware, right? So some of you might have heard, the new machine has 8 cores, right? 8 cores, which are not like the general purpose cores. I mean, it's not like 8 processor, power PC kind of thing. But for gaming, it's super. I mean, 8 of them can do stuff at the same time, and it has one power PC core controlling all the 8 cores, right? And each core is powerful enough to, so one of the demo that they were trying to do was each one of them can do 3 video chat at the same time. So if you have done video chat, right, 640 by 480, it usually brings a machine to its knees, right? So that you can do 3 or more video audio chat in real time at any single time with one core, right? And you have 8 of them, right? So you can actually have high definition video game going on with the video chat going on the side and stuff like that. So this is cool, whichever way you look at it, from a gaming perspective, but from an operating system perspective, right? So I'm saying here, yes, you have to worry about, having threads gives you this facility to use all the CPU. So now we are on steroids. I mean, you're basically having 8 cores or more, right? So the question was, what kind of operating system do these things run, right? Do you know, like what? So this is, so we're talking about a machine which has 8 cores. Each one of them is fully capable. So you're having a 8-way multiprocessor, right? It's not exactly general purpose, so it can't do all the stuff that you want, but it's still powerful enough to do cool stuff, right? So what kind of operating system runs on those? Which I suspect is the same on your PSP2s and stuff. I mean, the general games, right? Anybody wants to take a crack at it? It's not in the textbook, so your guess is as good as anything else. So you really want an operating system which is like really powerful, cool. It can do all this, all the stuff we're talking about, but much better, right?
Sometimes if they just create their own, it's kind of like not a very large kernel, and then they rely on the game developers to make it more efficient for what they want.
Yeah, actually, they don't have a kernel, right? They don't have a conventional operating system that we think of, right? So when you get this Sony hardware from Sony, they give you a library. The operating system is a library, so you get to use these cores to do different stuff, right? So the library gives you stuff like I can reserve a core and assign some tasks to it. I can run Linux on the main thing, and it can assign tasks, put memory and put programs on the different ones. But that's about it, right? So the biggest challenge that Sony faces is not to build this, this massive supercomputing thing, which is screamingly fast, but it's to get the game programmers to actually use this darn thing to do anything, right? Game programmers know how to use one core, right, which is trivial, right? Because one core, if you don't have threading, it's basically the process model we talked about. There's one thread of execution, no sharing, nothing. You're good to go, and you'll be 1/8 of what the hardware can do, 1/8 or 1/7 of what the hardware can do, right? So a good game programmer has to be an excellent OS programmer, because you need to. So now you are in complete control, right? If you do a good job of keeping all the 8 going, right, they don't know how this game will look, because they haven't actually been able to write a program, a video game which can use all the cores to keep doing stuff, right? But if you can, right, that's going to be an awesome game, right? So I just want to put it, as a thing to say, all these things we're talking about may seem dry in terms of doing threads and stuff, but that's sort of the future, right? With that, I'll kind of end today, and we'll continue on.